isomers are. Isomers are compounds that have the same molecular formula but will have different connectivity of the various atoms. So, for example, we have C6H14, and we have 3-methylpentene and 2-methylpentene. These two are considered constitutional isomers because they have the same molecular makeup, but they have different connectivity of their atoms. The next type of isomerism we're going to discuss is stereoisermorism. Now, like constitutional isomers, they will have the same molecular formula, but they will have the same connectivity of their atoms. The only difference is in stereoisomers, the spatial arrangements of these atoms will differ. In this example, we have these two hydrogens are drawn with wedges, which means they're coming towards you out of the page. And these two hydrogens, one is drawn in a wedge, one is drawn in a dash. The wedge means it's coming out of the page, and the dash means it's going into the page. Okay, now we're going to explain enantiomers. Enantiomers are two molecules that would be mirror images of each other. So, in this example here, we've got a modeling kit. The central atom, this black one, is a carbon, and the 4 different colors around it represent just various atoms. So these two are mirror images. If you're going to put a mirror right between them, you would see the opposite. Now, if you were going to try and superimpose one on the other, no matter which way you twist and turn, they would not be the same. On the other side, we've got diastereomers. The best example of diastereomers are cis and trans examples, and where cis in this one, the two R groups are on the same side of the double bond, and in this trans example, the two R groups are on opposite sides of the double bond. They're not mirror images, and they're not superimposable on each other.
Next, we're going to be explaining to you what chirality centers are. A chiral center is a carbon with 4 different atoms attached to it. For example, in this molecule we have the chiral center would be right here. This carbon is attached to a chlorine, a methyl group, an ethyl group, and then this hydrogen here. For this molecule, the chiral center would be here because the carbon is attached to this OH group, a hydrogen, a ethyl group, and then a propyl group. This molecule, the chirality center would be this carbon right here. It's because one path around the ring is different than the other path around the ring, because this path is going to encounter the double bond sooner than if this path were to go around. Versus this molecule right here, which doesn't have a double bond, so this would no longer be a chiral center. Before we get into RNS configurations, we want to talk about priorities. First, you want to establish where your chiral center is. So here's our chiral center. Then you want to, highest priorities will be given to the highest atomic number versus the lowest priorities given to the lowest atomic number. So you look at your atoms attached to your chiral center. We have chlorine, oxygen, carbon, and hydrogen. Chlorine has a highest atomic number, so it's given priority number 1. Then oxygen has the second highest priority, so it's given number 2. Followed by carbon, which is given 3, and then lastly hydrogen, which is given 4. So we have 1, 2, 3, 4. After you prioritize your molecule, you're always going to want to have your lowest priority on a dash. So you're going to have to rotate the molecule. So in this example, we're rotating it so that the hydrogen is now going to be in the dash versus the chlorine. So now our priorities go 1, 2, 3, 4. So now that we've established priorities and made sure that the lowest priority is on a dash, we can see whether our 1, 2, 3 sequence is clockwise or counterclockwise. So in this case, our 1, 2, 3 sequence is counterclockwise, so therefore it's given an S designation. Its enantiomer would have a R designation being clockwise. So counterclockwise is S and clockwise is R. Sometimes you encounter the problem where your chiral center doesn't have 4 different atoms attached to it. So for an example, in this molecule, you have a hydrogen, an OH, and 2 carbons attached. So how do you decide? First, you want to see what these 2 carbons are attached to. Okay, they're both attached to another carbon, right? But then what are those carbons attached to? This carbon only has a hydrogen, whereas this carbon has 2 other carbons attached to it. So this carbon attached to the chiral center would have priority over this one.
So now that we understand that chiral center contains 4 different atoms attached to it, and therefore the molecule is chiral. So the same is not true when we have 2 or more chiral centers. So in order to distinguish compounds that contain 2 or more chiral centers, we should understand symmetry. There's 2 types of symmetry: rotational symmetry and reflectional symmetry. Here we're gonna describe rotational symmetry first. Here we have a trans 1,2 dimethyl cyclohexane. So if we take one methyl group and rotate it 180 degrees, we will generate the same image. So therefore we have an axis of symmetry. So when we have cis 1,2 dimethyl cyclohexane, we do not have an axis of symmetry. We have a reflectional symmetry because the right side reflects the left side and vice versa. So chirality depends on reflectional symmetry. Now, a compound that contains 2 or more chirality centers and reflectional symmetry makes the compound achiral. Now, those compounds are called mesocompounds. Now, there's a simple technique to distinguish the mesocompounds. Here, on the molecule on the top, we see that we have 2 atoms going in the same direction. Now, if we divide the compound in half, we see that the 2 halves reflect each other. Now, this makes the compound achiral. Now, in this bottom molecule, we see the same characteristics. We see 2 atoms going in the same direction. So if we divide the molecule in half, we see that the 2 halves reflect each other. So again, it's an achiral molecule. Now, I'm going to explain one more type of symmetry. If we focus on every single point of a molecule, we see that for example, this molecule, we see that the top methyl group reflects the bottom methyl group. And we also see a reflection of symmetry in the molecule because the right side reflects the left side of the molecule. So therefore, it's a achiral molecule. So to do a quick summary, a compound containing 2 or more chiral centers and contains a reflection of symmetry makes the compound achiral. A quick recap about everything learned. Isomers have 2 types: constitutional, which are molecules having the same molecular formula but different connectivity. Now, stereoisomers have the same molecular formula and have the same connectivity but different spatial arrangements. Chirality are molecules having 1 carbon center and 4 different atoms attached to it. So enantiomers are chiral molecules that have mirror images of each other. Diastereomers are chiral molecules that are not mirror images. Now, symmetry, we have 2 types of symmetry: rotational symmetry and reflectional symmetry, which the right side reflects on the left side and the left side reflects on the right side. In configurations, R is clockwise and S is counterclockwise.
Hey, I just met you, and this is crazy, but here's my number, so call me maybe. It's hard to look right at you, baby, but here's my number, so call me
Means, because chemistry doesn't exist, it's all magic. I'm thinking about it. Isomers? No, hold on. We get into, no, what do we, that's the other one, stereoisermorism. Isomer is a compound, that's not right. Just discuss. I'm like,
A C. Okay. It is a lot harder than like you think
This
it is.
bro.
Ta-da! What you're gonna have to do is you're gonna have to awkward when people watch you. Suck it.